All right. Now, there are two special types of random variables that happen so often that we gave them their own names. They come up so many times that we decided, you know what, let's just call this something. So the first random variable that we're going to look at is binomial random variables. A binomial distribution. So far we've looked at normal distributions. That's pretty much it. Now we're going to look at a binomial distribution. And a binomial is a special type of random variable. The binomial setting you'll be asked about a lot. What makes something binomial? Well, only two things can happen. And for simplistic reasons, we'll say those two things are success or fail. A success is what is the variable that we're measuring, and a failure is that it didn't happen. But don't get hung up on success and fail and think that success has to be a good thing and failure has to be a bad thing. Oftentimes, a success will be death, or will be not passing the class, or it will be something in the real world that we think to be negative or a failure. In the binomial setting, a success is the variable that we're trying to answer the question for. So in order for something to be binomial, only two things can happen. And to make it simplistic, we'll say those two things are success or fail. Okay? So that's one of the things that must occur. Each individual trial must be independent of the previous trial. So in order for something to be binomial, only two things can happen, success or fail. Each trial must be independent. There must be a fixed number of trials. For something to be binomial, we need to know exactly how many times are we going to do this. And the final thing to make something binomial is that the probability of success must be the same each time. The probability of success never changes. Okay. So in order for something to be binomial, again, four things must occur. Only two things can happen. Binomial. Bi means two, right? Two things can happen. We'll call it success or failure. Each trial must be independent of the previous trial. There must be a fixed number of trials, and the probability of success is always the same. Okay. So just like before, it follows all the other probability rules. Really, all it is a random variable. Okay. Binomial setting, or the binomial random variable, can take a countable number of outcomes. That's why we have a fixed number of trials. Okay. So binomial, only two things can happen. We could think of having children, or the number of girls out of three children, as a binomial setting. Only two things can happen. You have a girl or you don't. The probability you have a girl, it's the same. It's 1/2 every time. There's a fixed number of trials. As we said before, we're going to have 3 kids. And the probability that I have a boy or girl is independent of what my previous child was. So that would be an example of a binomial distribution. All right, well, now that we know what the binomial setting is, let's look at an example of a binomial problem. For example, let's say that we are going to have 5 children, and we want to know the probability of having exactly 3 girls out of those 5 children. So let's say we're going to have 5 kids. Now let's change it this time, though. At least for me, all my children are girls. So I know the probability of having a male or female for me is not 0.5. I believe that the probability that I have a girl is 0.75. Okay, so the probability of success, in this case, a success is having a girl. Sorry, boys, but a girl is a success and a boy is a failure in this case. We're going to have 5 kids. The probability that any one kid is a girl is 0.75. And I want to know, what's the probability that I have exactly 3 girls? So if we first think about this problem, we'd say, oh, the probability that I have 3 girls, oh, that's pretty easy. That means I have a girl, and I have a girl, and I have a girl, and I have a boy, and I have a boy. So the probability of having 3 girls is 0.75 to the 3rd power, 0.75 cubed times 0.25 squared. Well, that's the probability that I have a girl and a girl and a girl and a boy and a boy. Well, that's 3 girls out of 5 kids, with the probability of a girl being 0.75 and the probability of a boy being 0.25. So at first glance, you might think, well, that's my answer. Let's think about why that's not the answer. Let's find the answer to this first. What's the probability my first 3 kids are girls and my second 2 kids are boys? Okay. Well, I already did the work here on the calculator for us. I took 0.75 cubed times 0.25 squared, and I got 0.02, let's just call it 0.0264 to round. The book likes to round to 4 decimal points, so let's call it 0.0264. So this probability is equal to 0.0264. That's a probability that my first 3 kids were girls and my second 2 kids were boys. But that's not the question I'm trying to answer. The question I'm trying to answer is, I have 3 girls in any order. Isn't there another way I could have 3 girls? They don't have to be 3 girls first. There's a few different ways that this could happen. So the probability I have 3 girls out of 5 children, let's see, how many different ways could I have 3 girls? Well, I looked at one way right now. I could have triple girl, double boy. Or I could have double girl, boy, boy, girl. Or I could have double girl, boy, girl, boy. There's only 3 ways? No, I bet there's more. I could have first a girl, then a boy, then a girl, then a boy, then a girl. All of these have 3 girls. Or maybe I have a girl and then double boy, double girl. Well, that's possible. Okay. Maybe I have a girl, a boy, and then 2 girls and then a boy. Maybe there's only 6 ways. Oh no, what about if I had a boy first? Oh man, this sucks. Well, I could have double boy, triple girl. Or I could have a boy with 3 girls sandwiched in between and then another boy. Or I could have a boy, a girl, a boy, a double girl. Or I could have a boy, double girl, boy, girl. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways that can happen. Well, since it doesn't matter which order I multiply, all of these answers would be 0.0264, 0.0264. So I could go back and add 0.0264 10 times, or I could do 10 times 0.0264, which gives me, move the decimal point over once, which is 0.264. So what did I find? The probability that I have exactly 3 girls out of 5 children is 26.4%, or the proportion is 0.264. So just over 1/4 of the time, I would expect to have exactly 3 girls out of 5 kids. Well, this over here really sucked. That took me a long time and a lot of thought to figure out how many different ways could I have 3 girls out of 5 children. And that's what this binomial coefficient up here is going to do for us. It's going to allow us to find this number 10 right here. This is called the binomial coefficient, the number of ways to arrange k successes out of n trials. Okay? And this may be new, this formula up here. We read this as n choose k. It's the number of ways to arrange k successes out of n trials. Okay. So let's take a look at how this works. Okay, I'm going to clear off all this chicken scratch so I have room to write using this n choose k. So remember that we did 10 times 0.75 cubed times 0.25 squared to get the 0.0264 answer. Okay? But we had to do all that work before. So if we look at this formula up here for the binomial coefficient, the number of ways in this problem, the number of ways to arrange 3 girls out of 5 children. Well, we take n factorial divided by k factorial times n minus k factorial. All factorial means is take that number and every number underneath it and multiply them together. So in this problem, n was how many children were we going to have? Oh, we were going to have 5 kids. So 5 factorial. How many successes do we want? Sorry, boys, remember in this problem, a girl is a success, a boy is a failure. I wanted 3 successes. That means how many failures were we going to have? Or in this case, how many boys? Oh, we would have to have 2 boys. So this problem would be 5 factorial, which means 5 times 4 times 3 times 2 times 1, divided by 3 factorial, 3 times 2 times 1, times 2 factorial, 2 times 1. So 5 minus 3 is 2. That's where 5 minus 3 equals 2. That's where this 2 factorial came from. Now, instead of multiplying all this out and dividing, let's cancel what's common on the top and the bottom. So they both have a 3, a 2, and a 1. So that leaves me on top with 5 times 4, or 20. And it leaves me on bottom, which is 2. 20 divided by 2, that equals 10. Much simpler than writing out all 10 possible combinations. So the binomial coefficient, this n choose k formula, is going to be very helpful for us. It's going to allow us to find the number of ways we can arrange k successes out of n trials. Or back to the example that we're using here, it's going to give us the number of ways we can have 3 girls out of 5 kids. Binomial coefficient. Now that we understand that, let's look at the binomial formula. This is one of the most beautiful formulas in all of statistics because it's simplistic in the way that it's made. It makes total sense. We looked at earlier that same example of having 3 girls out of 5 kids. So let's say that P is the probability of success. I wanted to know the probability that X equals K. Or in this case, I want to know the probability of 3 girls. Okay? So the formula says n choose k, which is what we looked at up here, the binomial coefficient, times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. So let's go back to the having girls problem. Probability of success. The probability that I have a girl was 0.75. Therefore, the probability of failure, those two must be complements of one another because this is a binomial setting in which only 2 things can happen. So together, the sum of those 2 events must equal 1. The probability of success was 0.75. The probability of failure was 0.25. Well, probability that X equals K. So in our problem, it was the probability that X equals 3. Well, first I need to find how many ways could I have 3 girls out of 5 children. And that's all the work that we see up above. That answer was 10. In this case, the probability of success or a girl was 0.75. Raised to, how many girls did I want? Oh yeah, I wanted to have 3 girls. Times the probability of failure, which is 1 minus the probability of success. Oh, that was 0.25. Times how many failures did I want, which was the total number minus the number of successes. So if I clean this up a little bit, it's 10 times 0.75 to the third times 0.25 squared. Oh, hey, I already did that up here. I already knew that that was going to happen. But this problem up here took me 2 pages and about 20 minutes worth of talking just to figure it all out and write it all down. So knowing this formula right here is going to save us tons and tons and tons of time. The probability that X equals K equals the number of ways it can happen times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. So it's a beautiful self-explanatory formula that shows us how all this works. Now, you're probably saying, yeah, it sounds easy while you're watching me do it, but try to do it on your own is a different story. Okay? Remember, the calculator is the muscle. The calculator knows how to do this. Okay? So we can answer these questions using the calculator, using the binomial function in the calculator. It's beautiful for us. Okay. let's go back to our same problem. What's the probability that I have exactly 3 girls out of 5 children? So I'm going to have 5 kids. A success is a girl, and the probability of that any one child being a girl is 0.75. So let's look at how to use technology instead of the binomial formula to find the answer to this. So I want to know, what's the probability that I have exactly 3 girls out of 5 children? Well, we're going to go into our distribution and we're going to look for binomial PDF. Okay, so in the calculator, they abbreviate it as binom PDF. We're going to call it BPDF, which stands for the binomial probability density function. Binomial PDF answers this question: the probability that x equals k. Well, for our problem, we wanted to know the probability that x equals 3. So let's open up this binomial PDF. And we need to know what to put in. Remember, the calculator is only as smart as the guy pushing the buttons. It's the muscle, we're the brains. We got to tell it what do we want it to do for us. Trials. Well, how many kids do we want to have? Oh yeah, we're going to have 5 kids. What's the probability of success? Oh, 0.75. And how many successes do we want? Oh, we wanted 3 successes. So paste. And you can see if you don't have the 84 plus or the 84 or above and you have an 83, you'll have to type this in, parentheses 5 comma 0.75 comma 3. You'll have to type that in yourself instead of it pasting it for you. And then just hit enter. Oh, 0.2636. Yeah, that's the same answer we got by working our way through the formula. So the calculator does all the work for us. It does the binomial coefficient. It does the probability of success times the number of successes. It does the probability of failure times the number of failures. It does everything for us and spits out the answer. But we have to understand what to tell it to do. So for binomial PDF, it answers, what's the probability that x is equal to k? Or what's the probability that x equals one given value? Now, what if the question that we were asked is, what is the probability that we have at least, or what is the probability we have 3 or fewer girls? Well, so what is the probability that x is less than or equal to 3? Which, and since this is a binomial question and there is a finite or fixed number of outcomes or a fixed number of trials, the fixed number of outcomes is because this is a random variable and it's discrete. There's a countable number of outcomes. This is the same as saying, what's the probability that x is less than 4? Because I can't have 3.5 kids. I don't care if she's short or skinny, or she's not a half a kid. Okay, you can only have a whole number of children. So these two are asking us the same question. What does it really mean? What's the probability that I have 0 girls? Or what's the probability that I have 1 girl? Or what's the probability that I have 2 girls? Or what's the probability that I have 3 girls? Now, I do not want to use the binomial coefficient and the binomial formula 4 times and then add all those answers together. No way, no how. Okay. Something I failed to mention earlier that's not true in mathematics, but has to be true for this formula and in a binomial setting, is that 0 factorial equals 1. I should have mentioned that on the previous page. 0 factorial equals 1. Okay. That's not true mathematically, but it has to be true for this formula to work. Okay. So in this case, I want to know the probability that x is less than or equal to 3. Or the probability that x is less than 4. Or in other words, what's the probability I have 0 or 1 or 2 or 3 girls? I do not want to do this problem 4 times. Way too much work, way too time consuming. Okay. I don't even want to use binomial PDF 4 times and then record all those answers and then write them down. I could. I already know the answer for 3. I could do this again and put a 2 in here and do it again in a 1 and do it again with a 0 and then find them and add them all up. Nah. We're going to let the calculator do all the work for us. So again, to find the binomial function, we go into distribution, which is second vars. And now I want CDF. I want the binomial cumulative density function. So binomial CDF, how many trials? Well, I'm going to have 5 kids. What's the probability of success? Well, 0.75. What do I want? I want you to find all the answers up to 3 and add them together for me. So I want 3. Notice I typed in the exact same thing I typed in for PDF, but now it's CDF. That's the only difference. It's going to give me the answer for 0, 1, 2, 3 and add them all together for me. So paste it in. Again, if you don't have the 84, you're going to have to use the parentheses and the commas and type this in yourself. Hit enter. Oh, so there's a 36.72% chance that I would have 3 or fewer girls. Okay. Binomial PDF finds the probability that X equals. Binomial CDF finds the probability that X is less than or equal to. Okay. So PDF, probability that X equals K. Binomial CDF is the probability that X is less than or equal to K. It does all the PDFs for us and adds them all up. Very, very slick thing to have. Makes our life much, much easier. Okay. One more thing I'd like to look at in using technology to find these binomial probabilities is, what if I wanted at least 3 girls? So what if the question was the probability of at least 3 girls? That would mean that I wanted 3 or more girls. Well, that would be the same thing as the probability that I have 3 girls, or the probability that I have 4 girls, or the probability that I have 5 girls. Again, I don't want to redo this over and over and over again. Oh, I forgot my X equals in here. Okay. I don't want to have to use binomial PDF 3 times, record all the answers, go back and add them up. Now, cumulative density function means that it starts from 0 and finds the answer up to a certain point. Well, we don't want that. We don't want the answers from 0 to 2. We want everything from 3 to 5. So that's fine. I can use 1 minus CDF to find this. So if I want the probability that X is greater than or equal to 3, I can do 1 minus binomial CDF of what I don't want. Okay. I don't want everything up to 3. So again, I'm going to have 5 kids. The probability of success is 0.75, and I don't want 0, 1, and 2. So 1 minus binomial CDF, 5.752. Let's go get our favorite muscle here, the calculator, and have them do some work for us. So I clear this out just so we can have a fresh screen to start with. Remember, we find all these distributions under the distribution menu, or second vars. I want binomial CDF. Oh, but really I don't want binomial CDF. I want 1 minus binomial CDF. So I better go back to my main screen, and because the calculator is only as smart as the person pushing the buttons. I want 1 minus whatever the CDF is going to be. Because remember, I want 3, 4, and 5. I do not want 0, 1, and 2. So back again to second distribution, binomial CDF, 5.7. Whoops. This time I have to change it because I want 3 in my answer. So I tell it, find everything I don't want and subtract from 1. Because remember, the sum of the probabilities of a probability distribution must always equal 1, or the sample space. The sum of everything that can happen has to add up to 1. So if I know everything I don't want, I can subtract that value from 1 to find the answer of what it is that I do want. So in this case, I don't want 0, 1, and 2. So do binomial CDF up to 2, which is everything I don't want. It will paste it. And again, remember, it's 1 minus. So enter, 0.8964. So the probability that I have at least 3 girls is about 90% of the time, 0.8964. Okay. Let's go back and summarize how to use the calculator for binomial distributions. Okay, let me clean up this page real quick for us so that we can just write this nice and clear and clean. This is something you're definitely going to want to put into your notes. a big star around it, highlight it, write it on the back of your hand, scratch it into your forehead, something, because this is going to save you hours of work. Okay. So if I want to know for a binomial distribution, the probability that x equals k, that is binomial PDF NPK. Remember, N is the number of trials, P is the probability of success, and K is the number of successes. Okay? If I want the probability that X is less than or equal to K, then I do binomial CDF, NPK. So I tell it to do the cumulative function and find everything from 0 up until that value. Now, what if I want to know greater than or equal to? That's where it's a little bit tricky. So that's when we use 1 minus binomial CDF in how many trials, probability of success. But in this case, it's 1 less than K. So this is going to be super, super helpful if you can understand how this works and what this means. These are the only 3 types of questions that we could answer within a binomial distribution. Okay. So take a minute, write this down, make sure you understand these 3. If not, ask me in class tomorrow. All right. I need Montillo to